Did you take an exchange for it? It was last year. Thank you so much for Don't worry, she'll probably that wasn't their part. I did that.
So our test in this class will be on next Wednesday. Next Wednesday. Chapters. So the by the way, so we went up to see my grandson. There's Xander. There's my wife. Oh, he's 18 months old, and he is starting to talk a lot. So we took him up this Fisher-Price airplane and helicopter from when our kids were young, and he said airplane and helicopter, which is for an 18-month-old, I thought was pretty good. He can't get grandma, grandpa right, but he can. But he can get airplane and helicopter. The funny thing was, I think it was that evening, maybe it was the next day, and he goes, airplane, I love you. Didn't say I love you, grandma, grandpa either. But he liked his airplane, that was sure. Anyway, he's a good kid. So I think I assigned this last time, so in case you didn't write it down. So this is due, yeah, well, I think I assigned it last time, but I couldn't remember for sure. Chapter 3, Section 2. Okay, so I've assigned that one already. Okay, it's going to be on Section 2.3 and 2.4 and 3.1 and 3.2. So let's write that out. So it's the Venn diagrams, which can get kind of interesting, and mostly truth tables with ands or ors. So it's 2.3, 2.4, 3.1, 3.2. I could possibly sneak in 3.3, but I'll just do it for that. So next Wednesday, because I'm giving it on Tuesday for the Tuesday-Thursday class, and they're ahead of you because you had Labor Day off. So we're going to move on to Section 3 now. And there's not a whole lot. We're going to do some more practicing. We're practicing with truth tables. We just have one more, what do I want to call it, operator, logic statement, and it's called the conditional. We'll also talk about how you can model and or statements using electric circuits. So that kind of goes to the computer thing about computers, logic computers. So the next logic statement is the if-then statement. So here are two examples that are obviously if-then statements because they have an if and they have a then. So the first example is if it is breathing, then it must be alive. So we have two statements. We have statement A or P, we'll call it statement P. So statement P would be it is breathing. And we have statement Q, which is it must be alive. And so there are truth tables associated with this kind of question. You know, we could say if the statement is true when they're both true, meaning if it is breathing, then it must be alive. We could do if it is not breathing, then it is alive. If it is not breathing, it is not alive. Or we could say if it is not breathing, then it is not alive. Well, there's the combinations negations and not negations. So there's 4 combinations, just like there are 4 combinations for and or statements. Now we're going to use a different, of course we're going to have to come up with a different symbol to represent this particular word combination. And then you have another if-then statement here. If you are a Marine, then you love boot camp. So in this case, statement P would be, you are a Marine, and I guess that's with a capital M. Sorry if anybody's a Marine. You're a Marine, and statement Q would be, you love boot camp. Again, both of these statements can be true or false. So the symbols we use this arrow. So if you see P arrow Q, we write that or we read that as if P then Q, or in this particular case, when P is it is breathing and Q is it must be alive, we would be able to read the statement as if it is breathing, then it is alive. So we could say if P then Q. You can also say P implies Q, meaning that if this happens, it's implicit or implies that Q is true. Q happens. And we have names. We call P the antecedent and Q the consequent. We probably won't use that terminology much, but they do have special names. We'll probably say this is the first statement, this is the second statement. We won't use antecedent and consequent. This is just to remind me, if you look in Excel, you'll find out that there are if statements, if this, then that. So the way it works, if you've ever used Excel, the if statement has a test, meaning if entry A is greater than entry B, then if that statement is true, then you do the first line. If the statement is false, then you do the second line. So you might say, if 12, or if A is greater than B, and then if you have specifically A is 10 and B is 5, then that statement would be true, and you might do some kind of use one calculation if it's true and another calculation if it's false. So they're used in Excel, used in computer programming a lot. Okay, before we actually deal with truth tables, there are some cases where you have sentences that do not appear to be if-then statements, but they are if-then statements. You can rewrite them. They sound a little bit wordy, but by putting them as if-then statements, then we can identify what statement P is and what statement Q is more readily. So we've got these two kind of silly statements here. No guinea pigs or scholars. So another way of writing that is if one, and we use one to kind of, when we talk about something that's not a person or myself, if one is a guinea pig, spelled wrong, then one is not a scholar. So I've had to take the no part here and include that in the second statement, because you wouldn't say if one is not a guinea pig, then one is a scholar, because that wouldn't really represent the same. Oh, who said that? Okay. Oh, she's probably on the wrong. So who was it again? Oh, Timber. Oh, Timber, yeah. I just said Amber. That's what I'm sorry. Okay, she's probably in the wrong room. So tell her she's probably in the Stephen Nicholson room instead of the, it's the one that says, yeah, it's at the bottom of the page. So she hasn't done it online yet, so she probably went to here, to here. She needs to go down to the bottom right there. Where, yeah, under scheduled sessions. Okay. You got it? We can take a picture. Okay. Technology. You got a picture yet? Okay. So anyway, I've rewritten this to have the same meaning. So if one is a guinea pig, then one is not a scholar. The second one is an opium eater cannot have self-control. Again, it's not an if-then statement, so I'm going to rewrite it as an if-then statement. So if one is an opium eater, then one does not have self-control. So you got a couple of examples like that where you have to think about what they're saying and fit it into an if-then statement that has the same meaning. Which reminds me of something. I'm gonna stop my recording for just a second. Not that I don't really need to stop. Okay. So anyway, this is opium, not cannabis. Anyway, the reason this sentence is in there is because in the latter part of the chapter we talk about certain kinds of logical arguments, and there was one that's called that's what it's exactly called. It has to do with C.S. Lewis. The argument, Lewis Carroll, sorry. Is that the same? That's a different guy. So the arguments of Lewis Carroll. And the argument, here's the argument that they give. For want of a nail, the shoe was lost. For want of a shoe, the horse was lost. For want of a horse, the rider was lost. For want of a rider, the battle was lost. For want of a battle, the war was lost. And so you've got all these different kind of if-then statements. Therefore, so these are all the if things. Therefore, for want of a nail, the war was lost. So it goes from just a nail through all these little different things ultimately. And it's kind of the same. I pointed this out in the other class. I'm going to point it out to you guys here. It has to do with math, so it's not completely, it's not, oh, is that what, yeah, so the same kind of deal. Or cable TV leads to whatever, that's the other one. So if you go to the Weather Underground and you look under hurricanes, so there's a hurricane, if you guys didn't know, there's a hurricane in the Caribbean. And its name, I don't know, but I will find out here shortly, Matthew. So what this website does is gives you all these different maps associated with hurricanes. And one of the maps is this, what's called the ensemble, something or other, something ensemble. So you've got all these little purple lines. And so what they do is they take, this is a particular type of computer model for looking at weather, especially for hurricane tracking. And each one of them is a slightly different initial values for things like air pressure and water temperature and air currents. And so they vary them just a little bit. And there's something called chaos theory, where you can, small changes in something can lead to ultimately large changes in something else. So for the case of this arguments of Lewis Carroll, the guy's horse, the nail in his horse ended up costing them the war. Okay. And so there's also that, feather dropping somewhere will cause something else to happen. Now, the probabilities of those happening are probably pretty small. The air currents make move this thing, which moves this thing, which causes blah, blah, blah. So these different purple lines are different solutions based on different initial assumptions on the model. And you see they don't all come to the same value. They come to different. And what they do is they take the average of all of these purple lines, which surprisingly to me, it ends up being over here. Why it goes all the way over there, I don't know, because it would seem like this is the average. So these are the individual calculations, and this is the average. So they must have got a lot of calculations that followed this path, which is kind of scary. And based on that, they come up with a best guess for the track of the hurricane. So what this plot is, and it's kind of, let me just turn the lights off for just a second. So there are actually 6 different colored lines for 6 different models that different weather services have come up with. So you have the GFS model, which is the red model, and it shows it going up along the East Coast, hitting North Carolina near Wilmington, and then going out to sea, and then coming back and hitting Boston. And then you've got these other models, and these are all averages of the models. And then you kind of, sometimes you believe more models than others, and when the different models come into agreement, then you have more trust. So down here you can see all of the models are pretty much on top of each other. So the chances that this hurricane is going to cause havoc in Haiti is pretty certain, and it's going to clip the edge of Cuba and then go up through the Bahamas. But once it gets to the Bahamas, there's much more uncertainty of what's going to happen. So it's kind of, again, if this happens, then that happens, that happens, that happens. You know, ultimately, it gives you a bunch of different choices. Another one, they also have they do a model intensity, meaning how high the winds are going to be. So this one actually increases in strength. All the other ones tend to decrease in strength as time goes along. And they tell you the time, how many hours from the current time. So it looks like 3 days after the current time. This one says it strengthens. These say it decreases and weakens. Okay. This one advantage of living in Covington. Okay, so here's the truth table for the conditional statement, for the if-then statement. So just like before, we have all the combinations of trues and falses for 2 statements, which is the 4 statements: true, 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 false, false, true, false, false. And then here are the results. This is the truth value for a logic argument that has an if-then statement. And the way these truth values are determined are by asking this question: did the person lie, or was the statement misleading? So I'm going to use a specific example to show you how 2 false statements can result in a true truth value, which seems kind of doesn't seem logical. So the statement we're looking at is, if you study hard, then you will get an A. So we want to look at the case where the first is true and the second is true, and whether, is the person mad? Because if you told somebody this is what you have to do to get an A, and you do that and then you don't get an A, then you complain, right? Or you get upset. So the question we're actually going to, rather than asking, did the person lie or was the statement misleading, I'm going to ask the question, are you upset? Or mad? Upset, question mark. Okay. So condition 1, you study hard, which is what the first statement says. and you get an A. Happy or sad? Or are you angry about that? Well, obviously not, because you did what was specified and you got your just reward. So in this case, I'm going to say happy or not upset. Okay, the second case is we have a true P statement but a false Q statement. So you study hard and you don't get an A. Not happy. Okay. Upset because I lied to you. I didn't. Maybe I didn't lie to you, but I misled you. It's kind of like there's a politics. Everything. I always have good sports and politics. I can come up with an example of everything. So I'll give you two. I'll give you a sports one and a political one. One is every time there's an election, if you look at it, except for maybe the presidential election, because you have somebody that you can make fun of and do other things. But normally, if you're looking at a congressional election where, you're not going to talk about their tax returns or their husband's infidelities or something like that, they always say, vote for me and you'll get jobs. Jobs. And that's all they ever say. Then they go to Richmond and they vote on things like gun control, prayer in the schools, nothing to do with jobs. You actually look at I did this because I wanted to see it. I went to the Virginia, you can look up all the laws. I forget what it's called. Virginia, anyway, it has a list of all the things they've tried to pass and all the things they passed. And you look at all that list, and about 2% are to do with jobs. 98% have nothing to do with jobs. So you promise jobs, you go there and do nothing about jobs, and then the people get mad at you because you said you're going to do something about jobs, but you never did it. And then the next time you go elected, you say the same thing because people don't pay attention to anything. They're doing other stuff. So they still vote the guy in because he promises jobs again and he doesn't do it. Okay, so that, you'd be upset about that. My sports analogy is, you're a little kid and you're playing on Little League football, and they say, if you come to every practice, we're going to let you play. You get to play some, and then you get to the game, and then they don't let you play. Oh, it's too close. We can't let you play. But you said if I practiced, I could play. Sorry. Yeah, that's right. So, as a consequence, because of my personal experiences with that, when I used to play basketball on a team and I was in charge, before the game started, I would put up a schedule. You play first quarter, you play second quarter. Everybody was scheduled for a specific time. Everybody got equal amounts of time, and when you were to come out, you came out, and everybody got equal playing time. Because otherwise, people think they're better than the other guys, and they're always, oh, play me, or nobody tells you to get out. So that was my response to that particular, and it still happens today, as you know, if you have any kids, or it might happen to you too. Okay, the third case is you don't study hard. So the first, you don't do the first thing, so the first thing's false, and you get an A.
So your discussion board assignment for today is I want you to write down what the legal definition for an argument is and put that online. So as you can see, it's a form of expression consisting of a coherent set of reasons presenting or supporting a point of view, a series of reasons given for or against a matter under discussion that is intended to convince or persuade the listener.
Now, the other person who studied may not like that, but as far as you're concerned, you're happy. I didn't have to study hard. He said I was going to have to study hard, and I didn't study hard and still got an A. Woohoo! you're not upset, okay? You're happy again. So that's why it's a true result. So even though you were false to start with, and because of the order and because of the promise, there's no problem. And then the final one is you don't study hard. And you don't get an A. Well, at that point, you may be upset with yourself because you didn't do what you're supposed to, but you're not upset with the guy who promised you this, if-then statement, the result. So you're not upset at me, okay? So again, it's true. The result is true, and so it's not a true, it's not true and false in the classical sense. It's true. I'm not upset. I'm happy versus false, which is I'm not happy. And that's how you end up with the truth table as such. So when you do logic statements involve if-then, if you have an if-then statement as part of a logic statement, all you have to do is just use this truth table, the rules that go along with the truth table. Otherwise, it's just like any other thing that we've done already with the other conditions. Okay, I already did that. Also, it says the use of the conditional convective in no way implies a cause and effect relationship. So that's kind of that. Yeah, I mean, it's just words. So we're not guaranteeing anything, or we may not, in terms of experiments or something like that. If you do this, then this scientifically is the result. And this is kind of the short. It's not really short. I have a shorter way of doing it. You can use the truth table, or you can remember these three statements. It's like in the AND statement. We said an AND statement is true only if they're both true. We said with an OR statement, the OR statement is only false if they're both false. So this is just another way of doing it for this particular logic statement. So it says if P, then Q is false only when the antecedent, which is the first statement, is true, and the second statement, which we call the consequent, is false. Otherwise, it says if the antecedent, which is the first thing, if the first statement is false, then the if-then statement is automatically true, and also if the consequent is true, then it's all automatically true. To me, I have a hard time following that. So the way another way of doing this is the way I do it, is for an if-then statement, the result is false only when the first term, only when the first, I'll say first statement is true and the second statement is false. So it's kind of like the same reasoning I used in the other ones. I specify the conditions, the combinations, such that it's kind of like the exception. 3 out of the 4 are true. The only one that's false is when the first is true and the second one is false. And then it's false. Everything else is true. So that's another way you can remember it. So make sure that makes sense. For an if-then statement, the result is false only when the first statement is true and the second statement is false. Yeah, that does make sense. I'm going to delete that. Make that more. Okay, we're going to skip. We'll come back to that one. Well, rather than, I'm just going to do a truth table before we go to the next one, which is basically just rewriting stuff. We've done that before, but let's do a truth table. And let's do, so this would be just slightly more complicated than we normally do. So if P, this is if P, then not Q. Instead of if P, then Q, this is if P, then not Q. So we're going to create a truth table. We need a truth table that has P and Q to get all the combinations of trues and falses like we normally do. And then we'll need three additional columns to handle the truth, the logic statement. We need as many rows. We have two statements, P and Q, so we're going to square that. 2 squared is 4 plus 1 for the header. So our size in this case is a 5 by 5, using the same rules that we used in the previous section. So the header row is going to be PQ, and the logic expression is if P, then not Q. Pardon me? Yeah, it's just like the and or the or. It gets the same. It gets its own column because we're going to compare these two truth values and put the result in the middle. So the first 2 rows are exactly what we've done previously. All the different combinations of trues and falses. And again, we use that pattern: true, true, false, false, and then true, false, true, false. And then the next step is we fill in the columns that involve either P and Q or not P and not Q. So here we have P, so I just copy what's in the first column into the third column. And for the not Q, we copy this, except we change the truth values from true to false and false to true. So this true becomes false. This false becomes true, and likewise, you get that. And then finally, we have to use the truth tables to compare these 2 columns. So the rule is the only time an if-then statement is false is if the first statement is true and the second statement is false. So we look for that first. So we compare these 2 columns and we look for where we have true here and we have false there. So we see it right off. So that's false. And we don't see any of the other ones. We see they're both true, false, false, and false, true. Those are all true. So those, again, you can look for the exception, which is the one that's not happening very often, which is this one. The only time an if-then statement is false is if the first one's true and the second one's false. And that's your result. Okay. So we'll do a more complicated one in a second, but that's kind of the way it was started. So really all we have is a new symbol and new truth table that we apply comparing the things on either side of it. Okay, so let's revert here back. So this is problem 28. And what you have is the letters S, P, and M used to represent the statements: she has a bird for a pet, he trains dogs, and they raise alpacas. And what we are asked to do is express the following compound statements in words. So we take basically the symbolic logic and we insert the words. So why don't we let's do the negations first instead of trying to do it all at once. So the negation of P, we go over to this, P represents he trains dogs. Therefore, the negation of P is he does not train dogs. That's easy because it's just, it's a simple statement. It's not it doesn't say all or some or something like that. Okay, so that's the negation of P. And you have the negation of M, which was, M is they raise alpacas, and they do not raise alpacas. Has anybody ever raised alpacas? Yeah, alpacas are kind of like, what's that? Oh yeah, they're cute and everything. But you know what what happened with alpacas is kind of like, has anybody ever heard of it had to do with tulips in Holland during like the 1800s? So they're growing tulips, and then these people started collecting tulips, and then the value went up for tulips because it was the tulip craze. And then all these people were like, oh, I'm going to spend all this money on tulips. And then the market crashed, and people had these tulips, which really weren't worth any in the first place. So you have alpacas. What do you get out? What do you get off alpacas? Yeah, their fur. Whatever they call it. I mean, nobody eats alpaca meat, so it's not. I mean, you can either get fur, you can get hair, alpaca hair, or you can get alpaca chops, I guess. But nobody sells. They're too cute to eat. They probably do taste bad. So. Is it? Okay. So anyway, so what happened was people started buying alpacas, and they're like, oh, we ought to get into alpacas, so we're going to buy alpacas, and then the price goes up. Oh, I'm going to sell you alpaca for $1,000, $2,000, $3,000. So people buying these alpacas, and they said it's like buying sports cards, buying baseball cards. But so they bought these alpacas, and they because the price is going up for alpacas. So if I buy an alpaca now, I can sell a year later for twice the amount, and I can make profit. So everybody starts buying these alpacas for the future value of alpacas, forgetting that the only thing you can sell off an alpaca is fur, is wool, and then you have to make things out of the wool, and therefore the things you make out of the wool are really expensive, and there's some limit on how much you're willing to pay for alpaca sweaters. So at some point, they finally realized that, like, this is stupid. Why do we, and then the market collapsed. And then the people all had all these alpacas that they'd spent too much money on. Who knows where they took the money from to pay for these alpacas. And then there's like, I don't even want these alpacas because I have to feed them and I'm not even getting anything out of them. So my brother, he has a couple of llamas and a couple of alpacas that people gave him because they were at least willing to pay for the food. And otherwise, you'd have to slaughter them because they're at some point. So it's crazy like that. How things like that can happen. So that's the alpaca crash market. As my wife says, I am a repository of useless information. I'll start saying that as you go. What? Anyway, I think it's interesting. So I can humor myself. Okay, so anyway, so what this is, if we write this out, is if I've got to put an if statement in there because you got the arrow. So if I'm good at Trivial Pursuit, if, which is not worth a whole lot, if he does not train dogs, so that's the negation of P, then. So there's the then goes before the next stuff. Then they do not raise alpacas. And this is an or statement, or, and statement S is she has a bird for a pet. Again, this doesn't necessarily have to mean any sense at all for right now, because all we're doing is trying to learn how to change symbolic logic into words and the opposite way. So we found the negations. You could do it if you could do that in your head. You might just be able to say, well, let's see, he trains dogs, so the negation of P is they do not train dogs. So you don't have to write this out. I'm just doing it so you see what's going on. Let's see, this is 34. These are three new statements. B is I ride my bike. S represents the statement it snows, and P represents the statement the play is canceled. So what we're going to do in this case is we're going from the written if-then statement to using symbolic logic. So we're going to need this arrow because we have the if-then part. We recognize that it snows is represented by the letter S, so we put S in there. And I ride my bike, so we look for I ride my bike. The corresponding letter is B, and so that's going the other direction. So it's what we've done before. It shouldn't be too hard. Okay. This is 37. So let's just try this one. Why don't you write it out? So go ahead and see if you can figure out what the symbolic logic associated with that. And notice where the if and then are. So here's I guess we should put if the play is canceled and if it snows. Then, so I had to put an additional if-then statement in there. So there's really two ifs. So we're going to use this. We're going to connect these two statements. They're before the arrow, and then this will be after the arrow. So anybody got the answer? Hartnett. Yes, you. So the play is canceled. What is that? Which letter is that? P. Okay. So P and, so we use this thing, and it snows, which is represented by S. Put those in parentheses, because that's the first statement. Then we use the little arrow. Then, yeah, a little squiggly thing, and B. So that's the right statement. Okay, we already did this one, so we don't need to do it again. So we're going to move on to a little bit more complicated expression. So we use the same rules that we used before. First thing was find the number of rows and columns. So if you go back to your notes, let's do the number of rows first. So see if you can figure out what the answer is without me doing it. And now we'll do a vote here. Why did I choose those numbers? So if you have two letters, you'd have 2 squared, which is 4 plus 1. If you have 3 letters, you have 2 cubed plus 1, which is 8 plus 1, which is 9. And if you have 4 letters, then you'd have 2 to the 4th plus 1, which is 16 plus 1, which is 17. So really those are the only choices that you have given the logic statements. I think there is one actually that has 6. So if you had 6, you'd have 2 to the 6th plus 1, which would be 65. But of course we wouldn't want to have to do that. That would be extremely big. So 5. Anybody vote for 5? Anybody vote for 9? Anybody vote for 17? So some people didn't vote. Why would 9 be the right answer? Mary. Yeah, the rule was you take 2 to the n plus 1. So in this case, n is 1. We have p, q, and r. So n is equal to 3. No, it's 2 to the power. Yeah, 2 to the power. So that's 9. That's 8 plus 1. So that's 9. That's how you get the number of rows. Okay, then you do columns. So if you remember your notes there, remember n is 3. So that's part of it. And then you have, you know, how many columns do I need to represent that logic statement? So that's an intermediate question. What I want you to do is give me the final answer, and I'll give you a choice, some choices here to vote from. So that's what we're going to vote. So you guys online, I'm going to ask the people online, see how many people are paying attention, so wake up. So how many columns do you think you need? Yeah, so let's see if anybody's answered online. Megan says 6. Oh, 9. 6, 6, 6, 6. They're all just, yeah. You are sheep running off the cliff right there. What do they call lemmings? Is that what the run off the cliff? So at least they are awake. They did answer, so that's good. Okay, so you have 3 plus 1, 2, 3, 4, 5. So you have 5. You break that up into 5. So there are 5 for the logic statement. This is all stuff you need to know for the test. Okay. So the total number of columns is 3 plus 5, which is 8. So we need a table which is 9 rows by 8 columns. And if I gave you something that was 12 by 12, you wouldn't need 4 of the columns and you wouldn't need 3 of the rows. So don't fill up the table completely unless you need to. But a lot of people will just keep filling out the table because they don't realize that. You know, the table is made bigger than you need it to, so you have to actually decide what to do, but you don't have to actually draw the table. It's supposed to help you out. Okay, so we're going to make the table. That was step number 2, make the table. And we said it was 9 by 8, so I need to make mine a little smaller than that. So there we go. So go ahead and make your table on your paper. And go ahead. So that's step number 2, make the table. Step number 3 is to fill in the first 3 columns. So remember, we have a pattern. If you want to go back and look at your notes, if you've got notes, fill in the first 3 columns. So, yeah, what's in the first 3 columns? We need a P, we need a Q, and we need an R. So go ahead and fill that out. Filling out these 2 tables is going to be a large part of the test. So if you don't understand what we're doing in class, you need to work the homework, and then if you still don't understand, come and see me. So I'm going to ask somebody here in a second what they have written down. So here's a little interesting, if you're finished already, a little political fact for the day. So over the weekend, somebody sent the New York Times a copy of Donald Trump's 1995 tax return, and he showed a business loss of almost $1 billion. A small loss, yeah, right. So who knows what he's lost in other years. I think that was the year his casinos were going belly up. And so what does Donald Trump do when he doesn't like something? He sues them. Okay, so he says, I'm going to sue the New York Times. But it turns out that the New York Times, a newspaper cannot be sued for doing that. The person who gave them the tax returns, if it was done illegally, they can be sued, but the newspaper cannot be sued because they didn't do the actual criminal bit. They don't know yet. There's some, well, it was that tax return when he was when he was married to his second wife. Buy her from? Yeah, she was the woman he was having before he divorced his first wife. That was his girlfriend, I guess, and then they got married, and then they got divorced. So some people say it might be her, but I don't think anybody from the IRS would send that out, because if they did, they would send out the ones that they have already. The other ones, they wouldn't just do that one. So it's probably somebody from the time that he was married to this other person.
It's sort of unfair that they're putting so much pressure on him, because even though it is a tradition, and I do agree with it, it isn't a prerequisite.
It's not a prerequisite, no.
People would reel it in and because either we can have one side turning into the protesting.
Okay, let's do Miranda. What's the first column? Oh, you're still writing out all the boxes? Okay. How about Morgan? Did you have anything in there? Or you? Okay. So we'll talk. So Morgan's going to help me here. I'm going to talk her through it. So if you remember what we did, yeah, you missed class the other day. So yeah. So what we did was when we have these truth tables, we fill out the first n columns, however many letters we have, with this pattern of trues and falses, and the purpose is to get all of the different combinations that you can have of trues and falses that are possible. So with two columns, you can have true, 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 false, switch the order, false, true, or both false. That's fairly easy to understand. And when you get to 3 statements, like this one, then you use a similar kind of pattern. The last column we're going to repeat. Well, not repeat, but just alternate them, because that's what we did before. If you look at the last column of the previous example, we just alternated them. So we ultimately have 4 trues and we have 4 falses. All of these columns always have equal numbers of trues and falses. And we're using a pattern so that we get all the different ways that you can have them arranged. So the second, we'll go back here, just like in this previous example, which was simpler. Okay, so there we alternated them, true, false. Here we did 2 trues and then 2 falses. So if we have a bigger or a larger number of statements, we do the same thing, but if we only did it twice, we wouldn't fill out our table. So we just do it again. So we go back to the same pattern, true, true, false, false. And you'll see there's 2 trues, there's a total of 4 falses and a total of 4 trues. So it's still a total of 8, 4 of each. And then we go back here. Well, you might say, well, I'll do 3 at a time. But the problem is that if you did 3 at a time, it wouldn't come out even. So you have to do even, you have to do groups that are, this is every time, so we can say every other one. Here we do it 2 times, so the next one would be 4, which is an even number. So we do 4 trues and 4 falses. And what that ultimately results in is that these are the 8 different ways that you can have true as the first, or true or false is the first term, true or false is the second term, and true and false is the last term. So you know, on the extreme you have all trues and you have all falses, and in between you have the different ways that you can. It's like taking 3 different people and you put them up against a wall. How many different ways can you arrange those people? If you were doing like a mugshot or whatever you call that thing when they line up. You know, if you're doing a lineup, how many different ways could I take 3 people and line them up against the wall? And it turns out there's 8 different ways you can do that. Anyway, so that's what the first part is. So for any problem that involves three statements, P, Q, and R, or any three letters, these first three columns are always the same. So you shouldn't ever get that wrong. You just write it down in your cheat sheet and say, for three statements, use this. For two statements, use the other one. And we never do four statements on a test because it gets too big. Maybe that's not true. I have to remember. That might not be true. If we have four statements, then you'd have another column. You might have P, Q, R, and S. And there's some homework problems that are associated with that. Okay, so that's just different combinations of trues and false. Okay, now the next thing we do is we take this logic statement and we put the logic statement in these 5 remaining columns. So we start at the right. So what do we put in this column? Well, that's the second thing. What's the first thing? Ignore this because this is going to be a repeat. R. Okay. Okay. What's the next thing we do? That error thing, right? Yeah, the error thing. Okay. So that's that. Now, this parenthesis is not doing anything except just grouping this stuff together. So we can put these two together. So we never include parentheses by themselves. So we put parenthesis P, and then what do we do next? The upside down, yeah, which stands for, do you remember which one it is? And or. And yes. And then the last column we fill out with this squiggly thing, Q. So that's my logic statement. So if we have a letter by itself, we just put, it takes up a column. If we have a negation, that's also a column. And then with all the logic statements, those are columns. So that's why we needed 5. Okay. Now, the next step is we look at the columns that are either just the letters or the negation of the letters, and we either copy these things directly if we have the letters like we do here or we have there, or we copy the columns but we change for the negation we change the trues to falses and falses to trues. So if I have R here and I have R there, what should I write in this column here? Yeah, which is okay. Yeah. So we just alternate the true false true false. Okay. Then we go to the next one, which is P. So what do we write in P? Yeah. And then this one, we go to this column but change all the trues to falses and all the falses to trues. So what do I write there? Yeah. Okay. Okay. So you finished 80% of the whole thing, which didn't require any logic at all. It just required us copying stuff in. Okay, then we do things that are in the parentheses first. So we're gonna compare these two columns, and we're going to put the result in this column. And you look at the operator, which you said was a AND. And do you remember what the rule is for AND? When is an AND only true? What's that? When they're both true. Yeah, okay. So we're going to look, all we're doing is going to compare these two columns. And I'm going to move my cursor down. You're going to tell me to stop when you want me to put a true. Okay. So to see the cursor coming down, okay, it's coming down. Okay, so those are the only two cases it's true. So the rest of them are false. Yeah. So that's the rule for AND statements. So we do that. It's false. It's false. Okay. Then the final thing we do is we need to apply the rules for the if-then statement, and we're going to compare these two columns because this is what's on the left-hand side of the if-then, and this is what's on the right-hand side. It's the whole thing. Now, the rule for if-then statement, do you remember what that was? It's only false if Yeah, the first one's true. The Harley says the first one is true and the second one is false. So we compare these two, and so again, you're going to tell me when I need to put a false there because that's the one case. So you compare. It's only false if the first one's true and the second one's false. So this one's false, right? True, false. So we're going to keep going down here until you see another example of true in the first column and false in this, that one. Oh, yeah. That one, right? Okay. All the other ones don't fit that requirement, so that means all the other ones are true. And that's the answer. That's the result of the truth table. Pardon me? Oh, the number of rows. You take the number of statements in the original logic statement. So I have a P, I have a Q, and I have an R. So that is N. N is the number of letters, P, Q, and R. So with 3, you take 2 raised to the third power, which is 2 times 2 times 2.
It's just a statement when you plug it in.
Pardon me?
It's just the
yeah. Yeah. Now that's why it's either 5, 9, or 17, because if N is 2, you get 2 squared, which is 4 plus 1, which is 5. This is the case where you have 3. This is the case where you have 4 statements. So it always has to be one of those. The next one would be, well, let me ask you guys, what would be the next possibility? So this is when N equals 2. This is when N equals 3. This is when N equals 4. So this has to be when N equals 5. So if I take 2 to the 5th power, which is, anybody know what 2 to the 5th power is? What's that? Okay, 2 times 2 is 4. 2 times 2 is 8. 16. 32. Yep. So you add 1 to that. So the next one would be 32, which would be a big table. But that's okay. So there we go. So do we have 204? Okay. This is what is an equivalent statement. It turns out. Well, actually, this is the negation. So how do you do the negation of an if-then statement? The negation of a statement is we just put a not there. So we don't just say not if-then or something like that. So it turns out the negation of an if-then statement is P and not Q. Now, so let's look into that a little more, because what they're saying is those two statements are equivalent to each other. And if two statements are equivalent to each other, they should have the same final answer for both truth tables. So the first one, we already know what the truth table is because we just did it a second ago. It's so 3 by 5, and we remembered we said the rule was the only time an if-then statement is false is if the first statement is true and the second statement is false. So this is, if you go back in your notes, you'll find out that the if-then statement or the truth table for an if-then statement is true, false, true, true. That's just, and that was based on, I'm going to be upset if I have these arrangements. There's actually a fourth column, which I forgot to do here. If I did the negation of if P then Q. So when I take the negation of this, so this is the term in the parentheses, what's the negation of this thing? Mary. So if I'm negating this, not negating it like canceling it, yeah, this becomes false, this becomes true, this becomes false, this becomes false. So that's the negation of this is the same as what I'm doing here. So that's the truth values for the negation of the if-then statement. So what I'm going to do now is I'm going to do this AND statement and see what I get as a result. So I need 5 columns, 5 rows, because I have 2 to the second plus 1. And I need 5 columns because I have P and Q, and I have, oops, didn't mean to do that. I have P and Q. Let me undo it here. So what did I say, 5 by 5. Grab that thing, move it down. So I'm going to do the truth table for this thing. So I'm going to have P, I'm going to have Q, and I'm going to have my logic statement. So again, the first 2 columns are the same thing. True, true, false, false, true, false, true, false. Then I fill in these columns with either the truth values for P or Q, which I've got P by itself here, so I just copy this column down. This one I take the negation of Q, which is false, true, instead of true, false, true, false. And then I use the AND statement. So the only time an AND statement is true is when, somebody remember that? Jackson. When they're both, so I'll fill in the blank here. So the only time an AND statement is true if they are both true, right? False doesn't make, anyway, so it's true. So this one is true, and all the others are false because I don't have, so you get that, and you compare this column with that column, and you see you have false, true, false, false, and I have false, true, false, false. So those 2 statements are equivalent. So if I have a if-then statement, and here's one, okay? If that is an authentic Rolex watch, then I'll be surprised. So let's put a then in there. So that's the original if-then statement. So how do I do it? How do I make a negation of that statement? Well, let's explicitly write out statement P. So statement P is that is an authentic Rolex watch. So that's my statement P. My statement Q is I am surprised, or I'll be surprised. Same thing. So now that I've identified P and Q, all I have to do is write it in this form. So what I have is P and not Q. So how do I write that? I say the negation of this original if-then statement is that is an authentic Rolex watch and I'm not surprised. So that's how it works. The negation of an if-then statement is an and statement where the second statement in the if-then statement becomes a negation. Trying to just figure out where to put a not. And notice the negation doesn't involve if-thens. It just involves the statements and the connector and. Okay, just did that. Skip all over that stuff. What I'm going to do is I'm going to officially assign this section for right now. What we'll do next time is we'll look at a few more truth tables. Again, good practice for the test. And we'll talk about electric circuits. But I think that's enough for today. So. I think we might talk about, we don't have to talk about it Wednesday, maybe next Monday, if I were putting together a cheat sheet for a test, what would I do? Because I think some people just don't have an idea of what the best way. And again, what you're doing is you're trying to look at all the homework that we've done and not just copy it down, but understand the process that's involved and the key things, whether it's writing down the truth tables for and or if-then statements, or whether it's writing down the rules that we just talked about in terms of if yeah, you get, it's all, I always let you take a cheat sheet. Let me make sure I got everybody here. Well, there's a lot of problems there, so I can get the online people. I'll just look at the list. James late, so I got to make sure I got him. And I think everybody else here was on time. Miranda was trying to confuse me by sitting in the back. At first I thought, is that Carrie? I don't think it is. I thought that was Miranda. Okay, now I'm gonna check the roll here. Turn off the record.